Okay, let us talk about Simon's algorithm. I almost said Shor's algorithm. Simon's algorithm is the first one we're going to go over. And I will first give some important things that we should be familiar for. So two important concepts, and I'm going to leave them on the side later so that we can consult them while going through the algorithm itself. So the first concept is this idea of partial measurement. So partial measurements. And the idea of partial measurement is that in these canonical circuit designs we have where we have some inputs to the top half of the register and we have some inputs to the bottom half, and we query it through some UF, and we get a top input and we get a bottom output. This bottom output being f of x. Then by measuring f of x, we inherently get some information about x, right? Because if we measure this f of x and we get a particular result, then there's only a limited set of x that could have caused that result. So by measuring the bottom output, we get information about the top output. And I think that'll be more clear when I explain with an example. So let's look at the case where we have x, f of x, and I'm going to make a tiny table right here. And in here, I'm going to put a 3-bit string set, and we're going to go through why we get information about x from f of x. So let's say x is a 3-bit string, and I'm going to put all the possible combinations of 3-bit strings here. Sorry, there should be a 1 now. Perfect, and there's still 110 missing as well. Okay, so that's 4, that's 8 possible combinations. And let's say f of x is 0, 0, 1, 1, 1, 1, 1, 1, 1 here as well, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, and 1, 0, 1. Okay, so now if we have this mapping that is captured in this query right here, this oracle, this black box function, when we query f and we measure the bottom output, which is f of x, we get information about x. So for example, if we measure f of x and we get a 1, 1, 1, or let's say before we get a 1, 1, 1, let's say f of x is equal to 1, 0, 1. Then there's only a limited number of x that could have caused such an f of x. And that is specifically for 101, this x right here, which is 100. So we instantly know x is 100. And by measuring the bottom output, we've collapsed the top input to 100. So that's the idea of partial measurement. And let's look at it with another example. So if, for example, I measure the bottom register, which is f of x, and I get a 0, 0, 1, then, or let's not do 0, 0, 1 first. Let's do an easier example. Let's do 1, 1, 1. This is my f of x. If f of x is 1, 1, 1, then what do we know? F of x can only be 1, 1, 1 if x is 0, 0, 1, or if x is 1, 0, 1. Those are the two outcomes. If that's the case, then the top register must be either 0, 0, 1 or 1, 0, 1, both with equal probability, because we don't have any inclination to believe one is more likely than the other. So we say that x is now collapsed to a uniform superposition of those two possible inputs. So for 1, 1, 1, we had x is 0, 0, 1, and we had x was 1, 0, 1. So by measuring the bottom register, we found out information about the top register, which is the input, which was x. And we know it is a uniform superposition between 0, 0, 1 and 1, 0, 1. And the same way, if there were more than two values of x that map to one f of x, then it would be a uniform superposition among 3 x's, and so on. So basically, measuring the bottom instantly collapses information about the top, because you know only certain inputs could have caused that output. And this is possible. Actually, forget that thought. I was gonna say it's possible because we know UF, but we don't have to know UF for that to be true. Even without us knowing how UF works, just by measuring f of x, it's true that this collapses to that state. Okay, so this set right here can also be written as, if you break it down by qubits, like Q0, Q1, Q2, this is a equal superposition between the first two qubits, and it is 1 over square root of 2 coefficients, so that's a plus state. And the next one is a 0, and the next one is a 1. So this is the top qubit, input qubit, after measuring f of x, and we can rewrite it like that. So then you know specifically which qubits are we still uncertain about. The 0 and 1 are deterministic. We know they're going to be 0 and 1, but the leftmost qubit is still probabilistic. We don't know which one it's going to collapse to. So we can measure and get either 001 or 101 when we measure x. So that is the first idea of partial measurement. And I'm going to actually highlight this in a box and keep it on the side so we can reference it later during the algorithm, during Simon's algorithm. Okay, cool. Now let's go over the second concept. The second concept is in regarding to the Fourier sampling that's going to happen later. So this is just a mathing. This is not really intuitively necessary to the explanation. So if you want to skip, you can skip. I would stick around just really quickly though for this because it's not too complicated. But basically, for some set of inputs, let's say y is some 2-bit string. So it can be either 00, 01, 10, or 11. If you applied Hadamard to each of these inputs, you will get an expanded result, and that result has certain coefficients of a set of basis vectors. So let me write it out so you know exactly what I'm talking about. So if we applied Hadamard to this, so let's say we did h, and I don't know if I went over this notation last time, but this means you successively apply h n times. So we're going to apply h 2 times to both of the qubits. So y00 would be this set right here. This will give you the plus state, which is also equal to a uniform superposition over all the basis vectors. And you can, as an exercise if you want to, you can try writing these two out in vector notation and then do the tensor product, and you'll confirm that result if you want to, or you can just take my word for it. But this is what that expansion looks like. So when you apply Hadamard to 2 0 qubits, you get this expansion right here. The coefficient thing I was talking about, the coefficients of all of these vectors, all of these basis vectors, these basis ket vectors, is 1. It's a positive. It's a plus sign. So you can rewrite it as like +1 times 0, 0 plus +1 times 0, 1, and so on. I'm not going to write the +1, but just know that is the coefficient thing we're talking about. And there's going to be a pattern here that can be generalized to a formula, and that formula will be used later. So now let's say we apply Hadamard to 0, 1. That gives us the plus and the minus state. And if we expand that, we get 1/2 times 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. And now there's negative terms in here. And now we say the coefficients of each of these terms are +1 or -1, and it matters which one's which. But basically, when you use the formula I'm about to introduce, you can instantly know which coefficients are what sign based off of just looking at that formula. So that formula is specifically beta y equals -1 to the r dot y divided by square root of 2 to the n, or 2 to the n over 2. Okay, so let's break down this formula. So if we take some input string r, what we do is, let's say r is 0, 1. It's just some 2-bit string in this instance because we're working in the 2-bit space for now. If we take 0, 1, then we're saying that -1 to the 0, 1 dot y. Remember, r dot y is you do the inner product, r1, r2, and you XOR it with the, sorry, not r1, r2, r1, y1, XOR r2, y2. So you do the inner product after doing the ands between each of the index correspondence between the two strings. So if we were taking some sample r, which is 0, 1, and we put it with the first y basis vector, the first y basis vector we're going to say is 0, 0. Then we get 0 XOR 0, which is equal to 0. And by the way, these are the basis vectors we're going to do with each one at a time. So we did it with 0, 0, we got 0. So minus 1 to the 0 over 2 to the n over 2. And n in this instance is the size of the bit string, which is 2. So that goes away, and I think that's right. Yeah, that's correct. And we're just left with the coefficient is... Actually, I might be wrong about that part. Oh, sorry, it's not 2 to the n over 2. It is a square root of 2 and then that to the nth power, which is different. So it's square root of 2 to the nth power. And n is 2. So you square the square root of 2 and you get 1/2. So now the coefficient is 1/2. So now when we write it in terms of the basis set, we're going to have 1/2 times, and we have our coefficient on the ket 0, 0 vector, which is just positive 1/2. So now we are writing what if we apply Hadamard to r, this is what we're getting, and we're going to build it slowly. So now for r equals 0, 1, we're going to apply to the next y basis vector. The next y basis vector is 0, 1. So for 0, 1, if we do the bitwise inner product and we do the XOR, notice the 0, 0 and 1, 1 will multiply, and then we get a 1 in the end because we're doing 0 XOR 1 from right here. That's equal to 1. So now we have minus 1 to the 1 power over 2, because that square root of 2 to the n is going to be fixed for this r string. This is equal to minus 1/2. So now we have minus 1/2, 0, 1. Now if we do this to the next one, which is 1, 0, the next basis vector of y, we do 1, 0, and we do the inner product of that and 0, 1, which is the r string. So it's r dot y, remember? That will give us a 0 result because it's 0 XOR 0. So this will be a plus 1/2, 1, 0. And then finally, if we do 1, 1 inner product with 0, 1, which is r right here, then we're going to get 0 XOR 1, because the 1 and 0 multiply to 0, and 1 and 1 multiply to 1. This is equal to 1. So we get minus 1 to the 1 over 2, and we get minus 1/2 for the last portion, which is 1, 1. And then what do you know? This is exactly what we calculated right here. If we applied Hadamard to 0, 1, we got this expanded sequence right here. And now we just applied Hadamard to a general r. And using this formula for the general r Hadamard application, we have the expanded version of that basis set vector. So that is just some math that will come into play later. It's pretty important, and then we'll explain why it affects so much later. So let me delete this work right here. I'm going to leave this part up so you can reference this later. And then let me copy this portion over so you can kind of see the full application of this. Okay, so now let's encompass this in a box, and we will store this on the side. Okay, so these are the two concepts you needed to know. And with these two concepts, you should be armed with everything you need for Simon's algorithm. Great. Okay, so now let's move on to what Simon's algorithm is promising. So Simon's algorithm has this problem set up. So we are given some 2-to-1 function f. 2-to-1 function f. So what is a 2-to-1 function? And by the way, this function is such that it's an n-bit string, and it'll give us an n-bit string as an output. Okay, so there's also, oh, by the way, a secret string that we're trying to uncover here. So what is a 2-to-1 function? A 2-to-1 function means for the domain and the range, a range and or codomain, if you ever hear that term, they're exactly the same thing. This means that for every single output in the range, there's 2 inputs that map to that exactly. There's no more than 2 inputs. There's no less than 2 inputs. And what does that mean? Does the inverse of f exist if this is the case? It does not exist, because if we have the inverse of f, then this becomes the domain, this becomes the codomain, and then you're saying that 1 input goes to 2 outputs, which is not true. So this is not an invertible function. It's not relevant to the problem that we're posing right here. Just wanted to review that with you though. But this is the problem. So we have a 2-to-1 function f, so that for every element in the codomain, there are exactly 2 elements in the domain that map to that codomain element. Okay, so now we want to basically find s given this fact, and also given the fact that for this function f of x, we have this statement being true. F of x XOR s is equivalent to each other. So for some f of x, it is also true that if you took the bitwise inner product with s, remember this is exactly equal to x1 s1 XOR x2 s2 XOR and so on. If you took that bitwise inner product, that result, f of that result, is going to be f of x. And slowly, by sampling again and again and again, classically, we would figure out what s is, but it would take a ton of queries. It would take a ton of queries classically. So quantumly, we can do this in instead about O of n tries, but it's going to take more than n samples realistically. But it's still going to be linear, whereas for a classical query, it is, I think, somewhere in the order of square root of 2 to the n, which is an exponential problem. So we do exponentially better by using Simon's algorithm and solving it quantumly. Okay, so that is the function. So we're promised that there is a secret string s, and we're promised that this is true, and we're promised that it's a 2-to-1 function, and we're promised it takes an n-bit string to an n-bit string. So those are all promises in this problem setup. Okay, so the first part of the circuit is to have this register at the top. The register at the top has enough qubits to supplement any, to basically be able to write any of the possible values that you might sample, any of the x values, and you should be able to generate any single one of those x values. So like for a 3-bit, if we know that x or n is a 3-bit string, then there's going to be 3 qubits that are passed to the top and bottom. So for the top, we have an n-bit string, so we dedicate n qubits to the top, and we dedicate n qubits to the bottom because the output is n qubits as well, which is going to be our f of x. So we pass in n qubits to the top, and we get x, and n qubits to the bottom, and we get f of x. We're using the canonical circuit design here. But before we do that, we actually apply Hadamard to all of the inputs before querying. And the reason we do this is so that we get a uniform superposition over all possible inputs, and we can query everything at once. And that's the idea. Query as much as we can at once. Okay. So we're going to use now this idea of partial measurement in this circuit right here. So we applied Hadamard to the top set. So now we have our input register is in a uniform superposition over all possible x in the domain. So in all of this domain, we have every single x uniformly superimposed after applying this Hadamard transformation to every single qubit in these n qubits in the top register. Now what we do is we measure the bottom output, and sorry, let me make that clearer. We will measure the bottom output, and once we measure the bottom output, we instantly collapse the top input to a superposition between 2 qubit strings. So for f of x, because it is a 2-to-1 function, that when we get a unique value of f of x, then we know there are exactly 2 x's that could have caused that f of x, right? So that's the idea of partial measurement. Now we're using partial measurement from right here, and we're using the fact that it's a 2-to-1 function to get this result. So when we measure f of x, let's say, we measure f of x, and we're saying that it is now in a uniform superposition of some n-bit string r. and some n-bit string r XOR s. And how do we know it's between r and r XOR s? We know that because this is the promise from the function description as well, that for some f of x is going to be equal to f of x XOR s, right? So if we get some f of x, then we know that both x and x XOR of s could have caused f of x. There are two possible inputs for this output, and we know exactly what those two inputs and outputs are mathematically. We don't actually know the bit sequence yet, but we know it's x and it's x XOR s. So we're gonna write that as a uniform superposition between those two possible inputs, which are r and r XOR s. R, x, it's basically the same thing. R, we're using r instead of x because it is a specific one that we've isolated, and that would be confusing with the general x from earlier. So that's why we're using a different letter here. Okay, so now we have this uniform superposition. And what do we do after that? Now we apply Hadamard to all of the top input. Okay, so what does that look like? In the circuit design, and I'm building the circuit as we go, so do bear with me because I realize that's not the most intelligent thing to do. But I'm gonna put this past this measurement state because this happens after the measurement. After the measurement and after the partial measurement and the collapse of the top register to a superposition between those two qubit states right here, we apply Hadamard to all of the top register. And once we apply Hadamard to all the top register, what do we get? So let's make this a little smaller. Okay, so once we apply Hadamard to all the top register, remember one thing. Remember this is just a general n-bit string, n-bit qubit string, right? And actually it's a superposition between two n-bit qubit strings. And what do we remember from the second rule that we brought over? If we apply Hadamard to any qubit string that is of length n, we'll say of some y, where length of y is equal to n, then we use this formula right here to find the coefficients. So to find the expanded form of this input right here that is in the top register after measurement, we want to apply Hadamard, and we're going to use this formula to find all the coefficients. So for an n-bit string, there'd be n-bit basis vectors. So it'd be like 0, 0, 0, 0 plus 0, 0, 0, 0, 1 plus all the way until 1, 1, 1, 1, 1, 1, 1, and so on. And we want to find the coefficients of each of these basis vectors right here, because there's a cool fact once we do that. So if we expand that form, it's going to become really messy, and it's actually the expanded form looks like this, and I'm just going to write it out because doing that math is just total hell. It's 1 over square root of 2, which we take from right here, and then we apply Hadamard on both of these qubit string inputs, and we get this times 1 over square root of 2 to the n times the sum over all possible y of -1, and I'm consulting a resource here. There's no way I remember this myself. Plus -1 to the x naught XOR s dot y, and then we have that. Okay. I think that is correct. Yeah. Okay, so if we apply Hadamard in sequence to some y, and in this instance y is this top register input, which is a superposition between the two possible inputs for the output that we measured. This is the expanded form, and this expanded form essentially guarantees that for two cases, case where s dot y is equal to 0 if we do mod 2, that there is constructive interference in these coefficients right here, in this whole coefficient sequence right here. And if we do s dot y equals 1 mod 2, then there's destructive interference. And specifically, this whole term right here collapses on itself and it becomes a 0. So it is not possible, or it ensures that there is a complete filtering out of all basis vectors for which s dot y equals 1. So of that basis vector sequence, remember where we were adding all of these possible basis vectors, blah, blah, blah. Remember all the possible basis vectors in the n-dimensional space that we are, sorry, in the n-bit string space, not n-dimensional. It's much larger than that. It's actually the 2 to the n-dimensional space. In the n-bit string space, that if one of these basis vectors dot s is equal to 1, then the coefficient is a 0 and the whole thing goes away. And it's not, Hadamard applied to this does not leave it in a superposition of something in this state. So it has specifically a 0 probability amplitude of happening. And that's an important result for us. So basically that ensures that the following result after applying Hadamard to to this sequence right here will ensure that any basis vector that has a non-zero coefficient is such that s dot y is equal to 0 mod 2. And why is that an important result? With this, we get a linear equation every single time we query this quantum circuit. And that that equation that we get is linear in nature because s dot y is equal to 0 mod 2. If it was s dot y equals 1 mod 2, it wouldn't be linear in nature necessarily. So because of that fact, we get a system of linear equations by doing this each time. And if we repeat it enough times, specifically n minus 1 times, and basically n minus 1 times we will query the circuit separately. So the very first time we query, we measure, which is right here, we get this result, and then we apply Hadamard, and then we get this result, and then we can take that y that we randomly take. By the way, one more thing I forgot to say. When we apply Hadamard to this whole input sequence right here, we get all possible y such that s dot y is congruent to 0 mod 2. So we have to do one more measurement after that to actually select a y concretely. So now when we concretely measure the top register, we will get one specific y. It could be either this one, it could be that one. And once we get that y, we can proceed with the rest of the procedure of generating the linear equations. So now we have some s dot y1, let's say, s dot y1 equals 0 mod 2. And then we repeat this whole sequence again. We apply Hadamard to the top, we query, we measure, we apply Hadamard to the top, we measure, and then we get another y, let's say y2. And now we know s dot y2 is congruent to 0 mod 2. And just like that, now we have n minus 1 such equations. And with n minus 1 equations, there's enough equations to solve the unknowns, and it returns 2 possible solutions. One, it returns a trivial solution where s is equal to all zeros. And the other solution is the actual secret string s that we're looking for. And let's think about why all zeros is returned as one solution, because for f of x equals f of x, or sorry, actually a simpler explanation is just that if you have s right here as all zeros, then 0 bitwise inner product with anything is going to be 0, and then that's going to be congruent to 0 mod 2. That's the easier way to explain it. So we don't care about that result. That's the trivial solution. We care about this s prime where it's non-zeros. Unless, of course, the secret string really is just all zeros, but that's very unlikely in this scenario. Specifically, there's a 1 over 2 to the n probability that it actually is all zeros. So that is how you do it. And one more thing to note, when we're sampling n minus 1 times for linear equations, there is a possibility we get the same y as we got earlier, in which case then we have two equations which are multiples of each other, and we don't have linearly independent equations, and then we need to sample more equations, more than n minus 1. It might be n plus 3, it might be n plus 7. We have to keep sampling until we get n linearly independent, n minus 1 linearly independent equations. So do know when we're sampling randomly and we're measuring and we're getting some kind of y, we have to check that y is not a multiple of the others. So it can't be a junk result. So approximately it takes about O of n queries, but realistically you're sampling more than n times because of probability, just pure chance that you might get a linearly dependent equation, which is what you don't want. So quantumly it takes O of n queries, and then classically we said it takes square root of 2 to the n queries, because you just have to keep churning out possible x's until you finally get, for some x, we have the exact same f of x across another x, and then we know that x is equal to x prime XOR s, and also that x prime is equal to x XOR of s. I think actually no, that's not necessarily true. I think forget that part, but we know this statement is true, and then we can solve for s, but we would have to query enough times that it would be of this order, which is an exponential order. So that is the benefit of Simon's algorithm and querying quantumly to get our results.